Hello friends, today we'll start the next topic from matrix spaces, which is nothing but continuous function from one matrix space to other matrix space. Continuity of function from one matrix space to other matrix space. We are studying the continuity of real function from 11th standard. Then you have studied concept of continuity of real valued function of several variables, real valued function of two variables, real valued function of three variables in multivariable calculus. Now we'll generalize this concept. We will generalize this concept for matrix spaces. Okay. So firstly, we recall the definition of continuity of real function. Continuity of real function. Real function. Okay. So let x and y be in an empty set. Then real function f from x to y is continuous at a belongs to x, is continuous at a belongs to x if for any epsilon greater than 0 there exists some delta greater than 0 such that distance between x and a, that is mod of x minus a less than delta, implies mod of fx minus fa is less than epsilon. Means x is very near to a, implies fx is very near to f of a in terms of distance. Now we have this mod of x minus a is nothing but distance between x and a. Mod of fx minus fa is nothing but distance between fx and fa. And we have distance functions on matrix. So it is possible to generalize this definition for matrix spaces. Okay. So definition. Let xd and y row be matrix spaces. Then function f from x to y. Then function f from x to y is continuous at a belongs to x if definition is always if and only if condition. A belongs to f if for given epsilon greater than 0, for any epsilon greater than 0, there exists some delta greater than 0 such that distance between x and a, such that distance between x a less than delta implies distance between fx and fa. But what is distance between fx and fa is defined by rho of fx fa is less than epsilon. See here, this mod of x minus is distance between x and a in subset x of real numbers with respect to usual metric. Just I am replacing that mod x minus a by d of x a. And mod fx minus fa, that is the distance, usual distance in y. Y is the subset of real number. So we are replacing that by distance between fx and fa in y. What is rho? Is a metric. Rho is distance function on y. Now this is equivalent to x belongs to s delta a implies fx belongs to open sphere about f of a. For any x with the condition d of x less than delta, means x lies in delta open sphere about a in x, implies image of fx must lies in epsilon open sphere about f of a. Again this is equivalent to Okay. X belongs means whatever x may be, means f of s delta A is contained in s epsilon f of A. Okay. So f is continuous at A if for given epsilon greater than 0 there exists delta greater than 0 such that f maps open sphere about A with radius delta in open sphere about f of A with radius epsilon, whatever choice of epsilon may be. Again this is equivalent to S delta A is contained in inverse image of open sphere about f of A with radius epsilon. Okay. So this is generalization of that definition. Generalization of this definition. Okay. So once we study some concept, then its negation is also important. So note moreover, f is continuous. On X if f is continuous at each A belongs to X. Here, while talking about continuity, we are defining continuity at a particular point A, and then if that function becomes continuous at every point in that matrix space, then we say that it is continuous function on matrix space X. Okay. Negation. F is discontinuous at A, A belongs to X if for some epsilon greater than 0. Okay. If for some epsilon greater than 0, negation of for any epsilon greater than 0, if for some epsilon greater than 0 and any delta greater than 0, there exists X such that d of xa is less than delta, but rho of fx fa is greater or equal epsilon. This is equivalent to for any delta greater than 0, S delta A is not subset of f inverse of S epsilon f of A for some epsilon greater than 0. F is discontinuous at A if I take any delta open sphere about A, it must not lies in inverse image of some open sphere about f of A. Okay. In that case, that function is discontinuous. Okay. Now we'll take examples on this. So we'll take firstly simple example. Let XD be matrix space and I from X to X be identity map so that I is continuous on X. So since I from X to X is identity function, therefore Ix is equal to X for every X. For every X belongs to X. So let A belongs to X. A belongs to X. Then mod of the D of Ix Ia is equal to D of Xa. From this, for given epsilon greater than 0, there exists delta is equal to epsilon greater than 0 such that D of Xa less than delta is equal to delta implies D of Ix Ia is equal to D of Xa less than delta is equal to epsilon. Okay. And therefore D f is continuous, or I, sorry, not f, I is continuous at A belongs to X, where A is arbitrary. A is arbitrary, and therefore I is continuous at each A belongs to X. Therefore I is continuous on X. I is continuous on X. Now we will take every identity function is continuous. Remember, but on both sides, your metric must be same. Your metric space must be same. Okay. Keep this in mind. I is function from xd to xd. xd to xd. Okay. Now next example. Let xd and y row be metric spaces and f from x to y the constant function defined as fx is equal to, say, y naught for every x belongs to x, so that f is continuous function. On x. So here for a belongs to x and x belongs to x, mod of fx minus, row of fx fa is equal to row of y naught is equal to 0. Therefore, for given a belongs to x and any epsilon greater than 0, any delta greater than 0, if delta of xa less than delta, d of xa less than delta implies this row of fx fa is equal to 0, or row of y naught is equal to 0 less than epsilon. implies so that this delta doesn't depend on epsilon and a. Any delta works here. Any delta works. Okay. Implies f is continuous at a belongs to x, where a is arbitrary. A is arbitrary. And therefore, f is continuous on x. Or f from x to y is continuous at every point. F is continuous at every point. Next example. Let f from close interval 0, 1 with respect to usual metric to Ru be function defined as fx is equal to, say 0 if 0 less equal x less than 1, and it is 1 if x is equal to 1. X is equal to 1. So that f is continuous on close interval 0, 1 except 1. Except 1. Alright. So let a belongs to close open interval 0, 1. That is a not equal to 1. So see here, this is your 0 and this is 1. If I take a to be anywhere, whatever this a may be, then, or it may be 0, then choose delta is equal to, take 0 less than, delta is equal to minimum of mod of a minus 0 by 2, mod of a minus 1 by 2. Minimum. If a is 0, then a minus 0 gives us 0. So don't take that delta. Then I will take mod of 0 minus 1 by 2, that is 1/2, that is 0.5. And then if that a is near to 1, then I will get mod a minus 1 by 2. If a is here, then a is near to 0. Okay. So in this case, I am choosing this neighborhood. In this case, a, I am taking this one. And this case, I am taking this half part. Is it right? And for 0, I am taking that type of interval. Greater than 0. Then S delta A in 0, 1, S delta 1 in 0, 1 is S delta, or S delta A is equal to x belongs to x such that mod of x minus a, x belongs to 0, 1. Mod of x minus a less than delta. This is precisely a minus delta to a plus delta intersection 0, 1. Intersection 0, 1. Okay. and it doesn't contain 1. Okay, it doesn't contain 1, doesn't contain 1. Right. Geometrically you can observe what is your S delta A. In this case, for any x belongs to S delta E, mod of fx minus fa is equal to mod of 0 minus 0, because x is not 1, a is not 1. Okay, for x belongs to S delta A, x and a are not 1, implies mod fx minus fa is equal to 0, less than epsilon for any epsilon greater than 0. Thus, for any a belongs to close open interval 0, 1 and any epsilon greater than 0, there exists delta is equal to 0 less than delta is equal to minimum of mod of a minus 0 by 2 mod of a minus 1 by 2 greater than 0, such that mod fx minus mod of x minus a less than delta, that is x belongs to implies mod fx minus fa is equal to 0 less than epsilon. Okay. Is it clear? And therefore f is continuous at A. At A belongs to at any A belongs to. Okay. Now we have to discuss continuity about 0. 1. Case 2. For a is equal to 1, S delta A is equal to x belongs to 0, 1, such that mod of x minus a less than delta. This is precisely a minus delta to a plus delta intersection close interval 0, 1. Intersection this one for any delta greater than 0. Then S delta A contain 1. Okay. Then for x belongs to S delta A, x not equal to A, for x mod of fx minus fa, which is nothing but for S delta 1, I'll take here 1 minus delta 2, 1 plus delta, right? So fx minus f1, this will become fx is 0 minus 1 is equal to 1. This is greater than equal to epsilon for 0 less than epsilon less equal to 1. Okay. So for epsilon is equal to half, epsilon is equal to 0.9, any delta greater than 0. Okay. Thus, for 0 less than epsilon less equal to 1, any S delta 1 for and for any delta greater than 0, S delta 1 contain x such that mod of fx minus f of 1 is greater than epsilon, and therefore f is discontinuous at discontinuous at 1 belongs to 0, 1. So this is A statement, this is my B statement. From A and B, f is discontinuous only at 1. Is it clear? So thus, today we have studied definition of continuity from one metric space to other metric space, and we have discussed continuity of some function like identity function, constant function, and one real function. Okay, so with the discussion, today we'll stop our session here. In next session, we'll see the more characterization, more sufficient condition for continuous function. So that sufficient conditions also plays very important role while discussing the continuity. Okay, so till that, bye bye.